For internet, okay. It's okay. In internet there was a picture where the Cybertruck, Elon Musk's Cybertruck, what is the name? Cybertruck was called as the first derivative of car. So it was not funny for me yesterday, but today it's funny.
Derivative is an interesting word by itself.
Or second derivative, I don't remember exactly, but anyway.
Just the tangent of the curves.
That is derived from something, and that's true, because that's what we call in finance all these derivative financial instruments like options, forwards, futures. Those are derivatives because those are derived from other, more simpler financial contracts. Oh, nice. Okay, so we can now use this big board. Okay, so continuing about mathematics for data science. So what we did, basically, we used the three algorithms for minimizing the function of potentially more than one variable. So x can be a vector. This coordinates x1, xm. So we want to minimize a multi-dimensional function without any constraints. With respect to the unknowns, so typical notation, minimizing f of x with respect to the unknown vector x, which can be multi-dimensional. So we can, some people might can have dimensionality m and coordinates. And what we did, we basically designed three algorithms for it, all based on derivatives. So Newton, and the formula for that was so to compute the next point from the previous point, and now by the point I mean that's a vector, x1, and the vector of 0, because it's a multi-dimensional function. So if you prefer, we can put the 1 at the top so that's not to mix it with the coordinates. Here, minus the Hessian matrix inverse multiplied by the gradient vector at the point x0. So we have the second algorithm called quasi-Newton. When we replace our Hessian matrix by some approximation, matrix H, and I'm not going to go into details how that approximation is computed, just it's faster than computing the matrix of the second derivatives exactly, and we have gradient descent, which is the simplest algorithm, because it's not using or approximating second derivatives. All what it's doing, it's going in the direction of the negative gradient, distance alpha, that we need somehow assign. And people typically take it simple. In the context of machine learning, people just typically assign it as a constant number. Let's say they say, okay, alpha is equal to 0.025, and just use that constant. Even so, it's not the best idea, but that's simple. In some cases, you can basically adjust it, or you can even compute the optimal distance that you need to go. So some algorithms, especially in the context of deep learning, such as if you ever heard about stochastic gradient descent, Adams optimizer algorithms, they dynamically adjust this alpha, which is called the learning rate in the context of deep learning machine learning. So alpha is typically called the learning rate. And in the simplest case, we assign it as a constant. That tell us which distance we should go in the direction of negative gradient to come to a point x1 from the point x0. And as we try to visualize everything, so this is the idea. So when we want to minimize a function, so this is our coordinates x1 and x2, this is the function value. Cool. So what we do, we start from any point x0. Let's say I started from this point x0. So at this point, this is the function value, the point x0. At this point, we compute the gradient multiplied by -1, and we go in the direction of the negative gradient. So let's say the direction of negative gradient is this direction, so the alpha is equal to this, so we go to this point. Yeah, everybody with me, this is our point x1. At the point x1, we again compute the gradient, multiplied by -1, let's say this is the direction, and we go that distance, this is our point x2, and we continue until we converge to the optimal solution. That's all what those algorithms are doing. They are going from the current point in some direction. The direction in this case is just a negative gradient multiplied by the number alpha. In this case, it's a negative gradient multiplied by the inverse Hessian matrix. In this case, it's a negative gradient multiplied by some other matrix H, but that's always a direction. So this multiplied by this is a vector, this multiplied by this is a vector. So that tells the direction which to go and the distance in which to go. In this case, distance is just 1. Here it's 1, here it's alpha. That's basically how the steepest descent is doing, and of course, when you move from one point to the other, the function value is getting smaller, and so on. So here it's even smaller, and eventually we arrive at the optimal solution. One interesting characteristic, as you can understand of the optimal solution, the derivative at the point of minimum is 0, the first derivative. What it means in multiple dimensions that this hyperplane, that's a plane that is horizontal, is tangential to this point. So what it means, in our notation, the gradient at this optimal point is equal to 0. At this point, which is, let's call it x star.
So there's a slice of the area of 0.
Yeah, that's all what it is. So this is a property of the optimal solution. The first derivative, the gradient vector, at this point is 0. Just horizontal line if we're talking about one-dimensional function, or the hyperplane, which is horizontal if we're talking about multiple dimensions of our function. So all these algorithms eventually arrive to this point. Now one complication. So as we basically said, okay, the point of minimum is the point where the first derivative is equal to 0. Is it always the case? Because we may have a function like this. Okay, first derivative is equal to 0, not the point of minimum. Of course, function like this, first derivative is equal to 0, this is the point of minimum. Or function like this, where the first derivative is equal to 0, but this is a reflection point and not the point of minimum. How we distinguish between this, and that? This is really a point of minimum, this is a point of maximum, not the point of minimum, and this is a reflection point or the saddle point. So what can we do? And for that, we need to know something about the properties of the function f that we are trying to minimize. So which properties you think are important? And we already basically can infer which properties are important. Function should be what? As we are required to compute the gradient, our function should be differentiable. So we should be able to compute the gradient. We should be able to differentiate that function. Because if the function is not differentiable, we are stuck. So algorithm won't know what to do. If we cannot compute the gradient and give it to the function, to this algorithm, one of these algorithms, that's it. Algorithm will be stuck. For instance, if our function is like this, you know, this is a famous function called the absolute value function. So what is the derivative at this point? It doesn't exist. The function is not differentiable at this point. So if we want to minimize the absolute value function, and our algorithms is coming to this point, and want to move to the next point, so it needs a gradient. Gradient doesn't exist, our algorithm is stuck. So we want our function to be differentiable. That's the first requirement. Second, we want our function to be continuous. So if our function is looking like this, and after it there is a like this, it's discontinuous, it's automatically non-differentiable. Of course, discontinuous function is automatically non-differentiable at that point, so you want it to be function continuous to differentiable. 3, something else. How we distinguish between this function, this function, this function? So what is the property that allows us to distinguish between this, and that? So this property is called convexity. So this function is convex, this function is not convex, and this function is not convex. So we'll discuss what is that, but we want our function to be convex. So if the function is convex, we're able to find the minimum.
Українською.
Выпуклость. Yes. Well, we'll talk much more about it. So we want our function to be convex. What does it mean for the function to be convex? I actually put a definition of the convex function.
Українською.
Differentiable, differенціована суд.
Диференційована.
Диференційована. Так, ми повинні всюди змогти на це порахувати похідну. So, convex function. So what is the definition of the convex function? Let me put it here. So this is actually a formal definition, but in order to understand, we need to visualize it, as always. To understand anything, we want to visualize. So the definition says the function f is convex if for any point x1 and x2 and any number lambda between 0 and 1, this inequality holds. So this means that function f of lambda multiplied by x1 plus minus 1 multiplied by x2 is less or equal than lambda multiplied by x1 plus minus 1 multiplied by x2. So let's try to draw this. So we need to visualize this in order to understand what does it mean to be convex. The definition says that, but it's useless without the visualization. So let's draw a function and try to understand if that function is convex. So what it says, for any point x1 and x2, so let this be the point x1, let this be the point x2. And any number lambda between 0 and 1. So now let's try to write down this part of the function. So, what is lambda multiplied by x1 plus minus 1 multiplied by x2? So this is x1, this is x2. If lambda is equal to 0, we are at the point x2. If lambda is equal to 1, we are at the point x1. If lambda is equal to 0.5, at which point we are? In between, we are here. So if lambda is equal to 0.25 or 0.75, we are here. So essentially, when we change lambda, we move along this line segment. Yeah? So this is line segment, which is written lambda multiplied by x1 plus 1 multiplied by x2. We substitute different values of lambda between 0 and 1. You get point here, 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 anywhere. Everybody with me? This is just the equation of this line segment. Now we need to take the function of that. So let's say that lambda is equal to 0.5. This point, we compute the function value at this point. We are here. Yeah, that's a function value at this point. So this is the left side of our inequality. Now what is the right side of our inequality? Okay, function at the point x1 is here. So this is function value at the point x1. Function at the point x1, this is the function value at the point x2. Function at the point x1, function at the point x2, and now lambda plus 1 minus 1 multiplied by lambda here, so this defines this line segment. So this is this equation of this line segment, yeah? And we change lambda, we move between f of x1 and f of x2. For lambda is equal to 0.5, we are here. And what this says, if this point is below that point, the function is convex. Does it hold in this case? Yes. But of course, we need to verify it for every lambda. So now we need to verify it for every lambda, we need to verify it for this, okay, holds, for this lambda, okay, holds, and so on. And we also need to verify it for any points x1 and x2. If we choose x1 here and x2 there, and so on, that also should hold. And it will hold for this function. So this function is convex. How to explain it in the other terms? So if a graph of the function, this is the graph of the function, is below the line segment connecting the 2 points on the function, that function is convex. That's what essentially the definition says. The graph of the function is below the line segment connecting 2 points on the graph. That should hold for any 2 points. So for these 2 points hold as well. The graph of the function is below this line segment. Holds for these 2 points. The graph of the function is below this line segment. Holds for everything. The definition holds for all points x1 and x2. The function is convex. So everybody with me so far? Now, can we turn this definition into an algorithm to verify the function convex? We need to be able to understand. So this is the definition. We want to convert it into the algorithm to verify the function convexity. Because the definition is definition, but we need to have an algorithm that tells us, okay, this function is convex, this function is not. Can we do that or not? How easy is to do it for this definition? Can we convert it to an algorithm? Not easy, because our algorithm will need to verify every combination of the points x1 and x2. How many points x1 and x2 are there?
Infinite.
Infinite. So of course that's not a good algorithm that needs to visit infinite number of points. It will never stop. So we cannot really design a good algorithm based on the definition. Can we do something else? Yes, we can try to design at least another algorithm that is based on the properties of the Hessian matrix of that function. And for that we need another definition, what is the positive semi-definite and positive definite matrix A. And that definition is that the matrix A is positive definite if any vector, non-zero vector, pre-multiplying that matrix transpose and post-multiplying that matrix is greater than 0. Or let's say for the positive semi-definite is greater than 0. So if for any non-zero vector, this is always hold, for any x non-zero, this is greater than 0, matrix A is positive definite. Essentially, positive definiteness, positive definiteness is the extension of the positivity and non-negativity from scalars to matrices. How we identify if the number A is bigger than 0? Well, we can use the same idea. If you pre-multiply and post-multiply by any number x, so if for x multiplied by a multiplied by x is greater than 0, sorry, for any x, for any non-zero x, this is a positive number, yeah? Or the same here. If this holds, this matrix A is a positive definite matrix. So basically, this positive definite is extensions of the positivity definition for scalars into matrices. Nothing more than that. But A is a matrix now, so X is a vector, so getting a bit more complex. Here, of course, because any X multiplied by itself is a positive number, so that we have X squared here. Yeah, of course. If A is positive, this definition will hold, we have A as a positive number. Or the same is if you want to check what is called positive semi-definiteness, we call it non-negativity, greater than 0. Yeah, that's all. So we have these definitions. Why those are useful? Those are useful because if the Hessian of the function, this matrix of the second partial derivative is positive definite, we have strictly convex function. If the matrix, Hessian matrix is positive semi-definite, we have a convex function. What that means, again, what is Hessian? And let's start with a function of one variable. Hessian is second derivative. Oh, that's what we learned in school. If the second derivative of the function is positive or non-negative, that's a convex function. Why? If we plot y, if the second derivative of the function is greater than 0, why this is a convex function? Well, that's a Christmas party. So what can we do? Okay, now let's, if we want, let's start with examples. So the function x squared. What happens with the second derivative of x squared? 2. 2 is strictly integrated in 0, so x squared is a convex function. Well, it looks like this, of course. It's convex, so it's a decided definition, so it's always about the graph. And so on. And the same what we can do for other functions. So the thing is, we need to compute the Hessian matrix. And after check that we satisfy this definition of positive definiteness, positive semi-definiteness, and checking this definition is not easier than checking this definition. Because in this case, we need to substitute all possible vectors x into a definition to check that it's greater than 0 or greater than 0. Not an efficient algorithm either to check the convexity through the positive definiteness or positive semi-definiteness of the Hessian matrix. But at least we have an idea. And now we can actually define what is the minimum of the function. So the minimum, the point x bar is minimum of the function if it's greater than or equal to 0. The derivative is horizontal line or horizontal hyperplane, like here, like there. And our Hessian is positive definite or positive semi-definite, which means that it is true for this function, not true for this function, not true for this function. So this is going to be the point of minimum. First derivative is equal to 0. Second derivative is greater or equal, which is greater than 0. Again, tells that their line tangential is horizontal, but also through here and through here, and says that second derivative is greater than 0, which is only through here, not through there.
What's the difference between a convex and strictly convex?
Okay, so let's talk about convex and strictly convex. So, this function is strictly convex, this function is convex, because it has a plateau but not strictly convex. Which means that's still a unique minimum, but it's reached at this point and at the same at this point, so there is a plateau at the bottom. It still satisfies the definition. If you, or let's take the 2 points, let's say we take 2 points here, connect those, and the line connected this coincide with the graph with the function, still satisfies the definition.
So a flat line.
Convex, but not strictly convex, strictly convex. Yeah, you can, for strictly convex, you don't have the flat region, so it's the minimum, it's still unique, but it's reached at 1 point x. Here, that minimum, which is still unique, can be reached at multiple points x. And again, typically, this distinction is not that much, so yeah, strictly convex is still convex. We can still find the point of minimum. Still, derivative here is equal to 0 at the point of minimum, the same as here, nothing really changes that much, as people tend to prefer this to that, if possible. So, that's what I mean. So, if we can check that our function is convex, and we find the point where its derivative is equal to 0, first derivative is equal to 0, this is the global minimum of the function. If we find a point where the derivative is equal to 0, but the function is not convex, it's not a point of minimum. It can be a point of maximum, can be the reflection point, or something else. And this is especially important because, yeah, we may have functions that have this form, and that's what may help in data science. So this function is definitely not convex. You just find the points, those violate the definition because the graph of the function is above that line. Second. But what you know that our optimization algorithms, they start from some point and after that they go in the direction of the function decrease to find the solution. So what that means, if you start from this point, any of these algorithms will find this local minimum. If you start from this point, we will find this local minimum. If you start from this point, we will find this. If you start from this, we will find this, and so on. So in that case, if a function is not convex, your algorithms for finding a mean of the function may converge to different local optimas. This is local minimum, this is local minimum, this is local minimum, this is local minimum. And you have no idea how you cannot visit all local minimums, especially think about this as a function in the dimension million. You will never even if you have infinite time, you will never be able to find the global mean, which is here. Yeah, this is slightly smaller than that. But even in small number of dimensions, even in 10 dimensions, you will never be able to find the global minimum if you have multiple local minimums. So if the function is not convex, it's difficult to work with that function. That's our lesson. So we prefer not to minimize the non-convex functions if possible. And that's unfortunately what happens for neural nets. For neural nets, you have no choice. Your error function for the neural net will look like this. That's why training neural nets takes forever, because training neural nets is minimizing the error of the neural net, but the function, unfortunately, whatever you do pretty much, for most topologies, architectures of the neural nets, the function will look like this. That's why training neural nets will take forever, because it finds local minimums until your time is over. So if you have 1 day, it will just continue finding multiple local minimums for 1 day. After that, you need to stop your training of the neural net. If you have 2 weeks, it will go for 2 weeks. If you have 1 hour, it can just go for 1 hour, and whatever the best local minimum you find, you take it as the minimum of your error function. And that's why always, if you think about this function as an error function, and we want to minimize the error, which is typical in machine learning, and your function, your error function has this form, no chance that you will manage to find the solution, global optimum, in realistic time.
Is it like a practical possibility when you're doing this kind of stuff to bound the area that you're interested in exploring and like possible solution sets that you might actually apply?
If you can. So can you bound some of their axes? Potentially. But even if you bound, that doesn't really help much because the space is still infinite for every axis. If it's doesn't really matter if it's between -1 and 1 or if it's between 1 million and plus 1 million, it's still infinite number of points in between. And that's just 1 dimension. So when you have million dimension,
there are different sizes of infinite.
So what you can do, if possible, you try to design the architecture of neural nets to have a convex error function, which is really difficult. In that case, it only happens for small neural nets. Or you do different tricks. And essentially, that's what we do in neural nets. We use this algorithm to minimize the function because it's the simplest. It doesn't require second derivative. It's fast. And we essentially do a restart. So what we do, we randomly generate initial point, find the local minimum. We randomly generate, this is our point x0. We started from this, we found this local minimum. After that, you regenerate another initial point. Let's say here, you find this local minimum. And you continue randomly starting from different initial points, running this algorithm because it's simple, it requires only the gradient, no hashing. This is fixed to a number, finding optimal solution, doing restarts until your time is over. That's how training of the neural net goes, and of course we'll go into more details, but that's the idea. In neural nets, as in any supervised machine learning, you want to minimize the error function, and in neural nets, as we'll see, because you're taking a nonlinear function of a nonlinear function at every layer, you lose convexity pretty fast. Even if your activation function in each neuron grow convex, and so on.
So
It's something to think about.
So did you say you lose convexity fast?
We'll see that. So let me not talk about that because in that case I'll need to draw more, but we'll come to that. So for now, what we basically learned so far. So when we want to find a minimum of a function, solve this optimization problem, we have three algorithms, and for these three algorithms to work, that's are the properties of the function f that we are minimizing. We want our function to be continuous and differentiable, otherwise we cannot compute the derivatives, and our algorithm requires derivatives. And we want our function to be convex in order to find the global minimum of that function. If our function is not convex, we will end up with local minimas, and there are many of those. So all these things, properties of functions, are coming from the requirements of this minimization algorithm, which in each term require derivatives to be supplied to the algorithm. Okay, other questions? Another thing that I just put on the previous slide, which people somehow get scary, is Taylor series expansion. But for your information, just what is first order Taylor series expansion is the equation of that line tangential to our function f of x at the point x0. So when I draw this function and the line tangential, so the equation of this line is called the first order Taylor series expansion. And of course, for the function of one and one variables, it's written in this form. So function f is function value at the point x0 plus the first derivative, as we had before, multiplied by x minus x0. Remember, we had this equation, f of x equal to f of x0 plus the first derivative of x0 multiplied by x minus x0 for the function of one variable. So this linear approximation of the function f of x is called first order Taylor series expansion. We have written that equation, just we didn't call it that way.
The letter T
That's transpose. So this is now the gradient vector, transpose multiplied by x minus x0. So those are vectors. So you do the inner product, you multiply two vectors. Transpose of this gradient vector multiplied by that. So typically vectors are represented as their column vectors. So this is your vector. If you want to multiply this by another vector, you need to transpose this. Transpose gives you horizontal, multiply by vertical, and you do this. So this transpose is equal to this, multiplied by this, you just do the inner product. So which means that first coordinate of this multiplied by first coordinate, so first coordinate of this multiplied by first coordinate of that, plus the second coordinate of this multiplied by the second coordinate of that. It's called the inner product of two vectors, so the dot product of two vectors. Everybody familiar with transposition of vectors and matrices? Yeah. Now, second order Taylor series expansion. So if we, instead of using linear approximation to our function, use quadratic approximation, it's called the second order Taylor series expansion. In that case, our function approximation is a quadratic function instead of being linear. And this is the equation of that quadratic function. Of course, it has a second order term, quadratic term, and requires a Hessian matrix to be computed. Quadratic approximation is better than linear, but more difficult to compute because you need to compute the Hessian. And below there is an example of computing the first and second order series expansion. All to remember, this is the equation of the line or the hyperplane tangential to our function at the point x0.
And so what do you mean by better? Are you like order of magnitude better, or
well, let's
slightly better, or
let's draw. So what do we mean by better?
Because computing the Hessian metric it's not trivial, so you'd expect for it to be worth it, you have to be a lot better.
Yeah. So this is our function. So this is linear approximation, line tangential to the current point at the point x0. You see, it's very good here, but it's already works there. When you do a quadratic approximation, quadratic function can approximate our function much better. So you see the error is getting smaller, but you need to compute the quadratic term. What you do depends on you. So typically people just use linear approximation in the algorithms. Like here.
But with like,
But you have a choice.
But with like if you're iterating so many times, like it kind of doesn't matter what the specific error of the individual thing is.
Oh, it depends. So of course this quadratic approximation speeds up your convergence, but you need to do more computation at each iteration. So it will take a small number of iterations, but at each iteration you need to compute the quadratic term. Over here, it will take more iterations, but each iteration you don't need to compute the quadratic term.
And what's the order between iterations? Like 100 times more iterations? 10 times more?
Yeah, so basically so in that case we're talking about linear quadratic convergence. So what we mean by linear convergence? Let's say that at each iteration we are able to reduce the error 10 times. Yeah? Now if it's linear, so in iteration 1 you reduce the error 10 times. After in the second iteration you use the error 10 times. The third iteration you use the error 10 times. So this linear convergence after 3 iterations, the error will be reduced 1,000 times. Now, if you have quadratic convergence, at every iteration, you reduce the error by the square of this. Multiply by square of this. So even after 2 iterations, you got already much smaller error. So this is much, much faster. Of course, quadratic order of magnitude faster. Yeah, don't want to go into details of these convergence properties, but that's something what convergence means. So at every iteration you reduce the error by a certain number. In this case 10 times, or it can be 2 times, just can be 10%. In that case, if it's quadratic convergence, you just square that number. And of course because number is smaller than 1, the square of the number is much smaller than the number itself. Okay, so that's any other high-level questions. This is still tough. Now we'll probably briefly talk about how do we verify convexity of this positive definiteness, positive semi-definiteness in practice. Just want to give you some ideas. Because we still want to check that our function is convex or not. And for that we know, if the Hessian is positive definite or positive semi-definite, it's a convex function, but the definition of positive definite, positive semi-definite is not good to be converted into the algorithm. And there are better computational algorithms to check positive definiteness, positive semi-definiteness of a matrix. And I just want to give you a glimpse of those 2 algorithms that are mostly used. Very high level, but still is good to understand. Because we should be able to verify convexity. Okay, and we'll do it for small functions. So, as you know, if we have a function of 2 variables, this Hessian is 2 by 2 matrix. If we have a function of 3 variables, this Hessian is 3 by 3 matrix. Now, in order to verify positive definiteness, positive semi-definiteness, one algorithm is based on the principal minors. So what are the principal minors? Are the determinants of the Hessian matrix. And if we have 2 by 2 Hessian matrix, the principal minors are, so there are 4 principal minors. So first principal is determinant of this number, which is the number itself. Second is the determinant of this number, which is the number itself, and the third is the determinant of this 2 by 2 matrix. Anybody remembers how to compute the determinant of the 2 by 2 matrix? Okay, so determinant of this is equal, and there is a very nice illustration that I remember from so multiplication of these 2 numbers minus multiplication of these 2 numbers. So you multiply these 2 numbers minus the multiplication of these 2 numbers. Anybody have seen that somewhere? University?
Sure. You mean this picture? Yes.
Yeah, how to compute the determinant of a 2 by 2 matrix.
Exactly this picture.
Okay, now what is the determinant of the 3 by 3 matrix? This is much of 1. So that's for this. So that shows.
I'm writing down things to look up later.
Yeah, most things I don't necessarily want you to remember, I want you to understand. So the idea is behind those. So determinant of a 3 by 3 matrix is product of these 3 numbers multiplied plus the product of these 3 numbers plus the product of these 3 numbers. Nice. Minus product of these 3 numbers minus the product of these 3 numbers minus the product of these 3 numbers. I'm sure that you have seen some of them, at least at university mathematical or discrete math courses. Not that I want you to remember, just
What is
some ideas.
What is the determination of matrix?
That's, again, so determinant of a matrix, yeah, the formula is there. So what it means, how to visualize determinant, that's a good question. So I need to think about that. Can you visualize determinant visually? Maybe, maybe not. So I need to look that up. That's what I am not sure about the visualization of the determinant of the matrix. Because some things are easy to visualize, some things are not. For instance, if you talk about solution of a system of linear equations, can you visualize it? Oh, very easily, in 2-dimensional space. So you know, this is one line equation of line 1, equation of 22, intersection with the solution of system of linear equations with 2 unknowns. Yeah, everybody has seen that. This is x1, this is x2. And we can even guess what happens if there is no solution. Of course, these lines are going to be parallel to each other, yeah? Just linear combination of those. That's, some things are easy to visualize. Or how about 3 dimensions? In 3 dimensions, you have intersection of 3 hyperplanes. If they intersect at one point, that's a unique solution. If 2 of them are parallel, and blah, 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 so there is. So some things are easy to visualize, some things you need to think. For determinant, I need to look it up, if it's possible to visualize determinant in terms of these geometrical objects. Again, what you can think, essentially complete determinant is some sort of dimensionality reduction. So you reduce your matrix of 4 numbers to 1 number, which is determinant. You reduce your matrix of 9 numbers to 1 number, which has some special properties that, for instance, we use in this algorithm to check convexity. But in order to visualize, yeah, need to think and read if we can do it. Now, so what are the principal minors for 2 by 2 matrix? Determinant of this number, which is the number itself, determinant of this number, which is the number itself, plus the determinant of the 2 by 2 matrix, which computed this way. What is it? What are the principal minors for the 3 by 3 matrix? So this is much more complex. So for the 3 by 3 matrix, principal minors are this determinant, this determinant, this determinant, after determinant of this matrix, determinant of this matrix, determinant of this 2 by 2 matrix, and determinant of the 3 by 3 matrix itself. There are 7 principal minors for the 3 by 3 matrix, getting complex. For these, 3 principal minors, 1, 2, and determinant of the 2 by 2 matrix itself. So getting tough to compute. But if you want to check positive definiteness of a matrix, we only need to lead at some degree called leading principal minors. And leading principal minors are, in this case, there are only 2 leading principal minors and 3 principal minors. So this is a leading principal minor, and determinant of 2 by 2 matrix is a leading principal minor. For the 3 by 3 matrix, this is leading principal minor, and after that, the determinant of this matrix is a leading principal minor, determinant of this 3 by 3 matrix is a leading principal minor. So there are 3 leading principal minors and 7 principal minors. Sounds complex, I know. Let's do an example. So let's compute leading principal minors to verify the complexity of this 3-dimensional function. First, we need to compute its Hessian matrix, matrix of second partial derivatives, and this is the matrix which you can verify. So that's 3 minus 1, 0, minus 1, 3, 0, 0, 0, 5. And we can put 2 outside of the matrix, so, or you just may put it inside, multiply every number by 2. Now, so this is the Hessian matrix of this function of 3 variables. Now, what is the first as I said, leading principal minor is just a determinant of this component. Determinant of 3 is 3. Determinant of a number is a number itself. So that's why first leading principal minor T1 is 2 multiplied by 3. By 2 we have this 2 multiplied by the determinant of 3 is 3. 6 strictly greater than 0. Okay, we verified the first leading principal minor. Second leading principal minor is the determinant of this 2 by 2 matrix. 3 minus 1 minus 1, 3. And we need to multiply. When we compute this, we need to multiply by this 2 squared. So, determinant of this matrix is using this. So, determinant of this matrix is these two numbers multiplied by each other. 3 multiplied by 3 minus 1 multiplied by minus 1. Minus 1 multiplied by minus 1. So, we get 4 multiplied by 8, we get 22, strictly greater than 0. So, second leading principal minor is also strictly greater than 0. And after that, we need to compute the determinant of this 3 by 3 matrix, of the whole Hessian matrix itself, using this. So what it's equal to is equal to 3 multiplied by 3 multiplied by 5, minus 1 multiplied by 0 multiplied by 0, which is 0, minus 1 multiplied by 0 multiplied by 0, which is 0, minus, what is here, 0 multiplied by 3 multiplied by 0, which is 0, minus 1 multiplied by minus 1 multiplied by 5, and minus, and here is 0 in any case. And after you're doing this multiplication, you get 320 strictly greater than 0. So all three leading principal minor are strictly greater than 0, so this matrix is positive definite, and as a result, this function is strictly convex. Again, I don't probably want to go into much details, but that's an idea. You need to compute determinants, put those together to verify the convexity of the matrix based on this algorithm of the principal minors. That's to verify positive definiteness. To verify positive semi-definiteness, you need to compute not only leading principal minors, you need to compute all principal minors and verify that each of those is greater than 0. So in this case, you will need to compute 7 numbers instead of 3. There is another algorithm, which is, again, this algorithm is combinationally practical, but it shocks in high dimensionality of the matrices. So, again, interesting to look at, not that much practical. More practical algorithm is to use eigenvalues of the matrices. Anybody heard about eigenvalues? Характеристичные вектори, характеристичные числа матрицы. Again, just basic understanding, so you don't need to remember that either. So, what is the eigenvalue of a matrix? So any number lambda is called, which is a solution of this equation for the matrix A, and any vector x is called the eigenvalue of the matrix. And in order to solve this equation, so what we do, A multiplied by x minus 1 multiplied by x equal to 0, that's the equation that we need to solve. So when we put x outside of the brackets, A multiplied by lambda multiplied by identity matrix multiplied by x equal to 0, and because x is non-zero, this equation will only have a solution if the determinant of this matrix is equal to 0. So essentially what we need to do, we need to solve this equation. Determinant of our matrix A multiplied by lambda multiplied by the identity matrix is equal to 0. So when we are able to solve this equation, we get this unknown vector lambda, the vector of the eigenvalues, характеристичные числа. And if all the eigenvalues are strictly greater than 0, our Hessian matrix A is positive definite. If those are greater than 0, it's positive semi-definite. So we can try to do the same for the same Hessian matrix. So how we do that? So so we need to solve the equation. Determinant of the Hessian matrix minus lambda multiplied by the identity matrix is equal to 0. So we need to compute the determinant of this matrix. So 3 minus lambda multiplied by 1, that's here. So essentially we need to subtract lambda from the main diagonal of our Hessian matrix, because identity matrix has only ones at the main diagonal and zeros everywhere else. And the rest is our Hessian matrix. And after that, when you compute the determinant of this 3 by 3 matrix using this formula, you get a cubic equation, unfortunately. So you get this cubic equation, which you can solve and find 3 solutions. So you can collect the terms, and you will get 5 minus lambda, lambda minus 2, lambda minus 4 is equal to 0. So the eigenvalues of this matrix is 2, 4, and 5, all are strictly positive. So this is a positive definite matrix. Wow, that's the same that we verified previously. In Python, you can do it better. You can just put in this matrix, compute the eigenvalues, and you get the numbers. Unfortunately for us, Hessian matrix is not always a matrix of constants. So when is Hessian matrix is a matrix of constants? For which functions? Hessian matrix is a matrix of second partial derivatives. When second derivatives are numbers. For linear function, are second derivative numbers?
No.
Yes, why not? When you compute the second derivative of any linear function.
Zero.
Oh, you get zeros, of course. So when you compute the second derivatives of quadratic function, are those numbers?
Yes.
Yes, derivatives of quadratic function are numbers. But if you have logarithms, exponents, and things like that, second derivatives will still contain variables. That's a problem. So Hessian matrix is not necessarily a matrix of constants. We were lucky because our function was quadratic function. So that's why there is a problem. Hessian matrix may contain variables itself. And verifying positive semi-definiteness and positive definiteness in that case is really, really difficult. What else can we do? And we can do other things. There are some interesting properties of the functions that makes it easy to verify the convexity. And those actually are very, very intuitive, and let's try to visualize those. So, if function f is convex, function f multiplied by any non-negative number alpha is convex as well. Why? Let's draw. So if this function is convex, what do we get by multiplying that function by a number, let's say 2? Yeah, it's either going to shrink like this, or it's going to expand like that, yeah? Doesn't change the shape of the function, still convex. Everybody with me? So very intuitive property. So if the function f is convex, let's say 25 multiplied by f is also a convex function. Okay? Or if it's a negative number, it doesn't hold. So if you multiply this function by minus 1, you get it like this, yeah, it's no longer convex. Now, sum of the two convex functions is convex. So if f1 and f2 are convex, their sum is convex. An example. So x squared plus the exponent of x. Is it a convex function? So this is a function f1, this is a function f2. Let's do it. So x squared convex, not?
Yes.
So you compute second derivative, it's equal to 2, strictly greater than 0, convex Hessian matrix, which is just a number in this case. Convex. How about the exponent? Again, if you don't know, let's compute the Hessian. What is second derivative of the exponential function? It's the function itself, yeah? So what we can tell about the function f of x? Is it strictly greater than 0? Yes, of course. So its Hessian is always positive. There's a convex function as well. Everybody with me? That's a second derivative, which just happens to be the same function. Okay, now sum of the two convex functions, so this whole function is also convex, as being the sum of the convex function. Everybody with me? So, when you need to verify something like that, those are very useful properties. So don't be scared that you need to compute the Hessian of this function. You don't. You can just compute the Hessian of this simple function separately, this simple function separately, and you know that each of the functions is convex, their sum is also convex. Again, always think in these terms. So there is no difficulty in mathematics as soon as you understand what the functions are, and if you know how to compute the derivatives. Everything else is very, very intuitive. At least when we apply it to data science. Maybe mathematics for, I don't know, for putting the man in space in the SpaceX program by Elon Musk is much more complex than this, but for data science, mathematics is not really complex. It's not beyond our understanding. Another property, which sounds really complex, but there is nothing. Affine transformation of domain, if f is convex, f of a x plus b is convex. So what it means, if f is convex, f of 25x plus minus 36 is also going to be convex. Affine transformation of the domain. It sounds complex, but this is just what it means, affine transformation of the domain. So what you tell, if the function f is convex, and instead of x you use any linear function of x, that's going to be the convex function as well.
But why do we care?
About convexity,
Just because to
just because of this. So this
whether
is
we can minimize.
this is the primer algorithm which is covering machine learning, as we'll see later, minimizing the function, and which is covering optimization itself. And those are pretty much optimization algorithms. That's a main algorithm in data science. Used in optimization modeling, used in machine learning. So in machine learning, we will be minimizing the error function. We still need to understand what is the error function, how to write it down, but we want to find a unique minimum. We want to find the point where the error is smallest of our machine learning algorithm. So that's what we will be doing behind the scenes in any machine learning algorithm. In regression, we will see how, in decision trees, in neural nets, and when we come tomorrow to solve this problem for machine learning, that's what we'll need to understand. What is our function f? When we write it down, can we check that it's convex? If yes, how? Can we check that it's differentiable? If it's not differentiable, what do we do?
How do we check whether it's differential?
That's a good question. So you basically need to look at the properties of that function. And the answer is simple. So if the function has a kink, it's not smooth function, it's not going to be differential. So absolute value function has this kink here, non-differential. You'll see some other typical functions which are non-differential. But you can verify differentiability
By visualization.
yeah, typically that's what you do. You look at the you just, you know for the typical functions whether those are differentiable or not, and that's it. So and people try to avoid using functions which are not differentiable. So pretty much in data science you will not find functions which are not differentiable. But to understand why, well, that's the reason. People just don't use functions which are not differentiable. For instance, why, when we talked about the error in the morning, so we decided, we want to minimize this error function, some of the errors between our variables and predictions in each of the examples, from 1 to 100. That's a function that we want to minimize. And we said, okay, this square is error. Now that's what we'll, of course, do in much more details tomorrow. But this is an example of that function f of x that we need to minimize. This is the error function for a machine learning algorithm. We want to minimize the error for each of the 100 examples that we have in our machine learning dataset. This is the target variable, this is the prediction of the model.
Makes sense.
Now, why people use squared instead of the absolute value function? Why people tend to avoid this? Minimizing this function and why prefer to minimize that?
Because it put a kink at 0.
Yeah, exactly. This is non-differentiable point 0. The absolute value function is non-differentiable point 0. Well, this is a quadratic function, convex. We can verify its convexity. Of course, it depends on this. But if it's convex, we know that it's all everywhere differential. It's a quadratic function. So that's why we would prefer to use this error function as compared to this error function. Again, that's all will be more obvious tomorrow. But today, in order to understand all these things tomorrow, we need to understand this right now, unfortunately. So we need to go through this boring stuff today in order to project it to the practice of the machine learning and optimization algorithms tomorrow. That's all. Otherwise, you would not really understand what all this means. But it's not actually, this is not as bad because there is a trick, which I didn't want to basically go into that, so there is a trick. So what is, this is our absolute value function. Yeah, this is x, this is y, this is just, so there is this kink here. So the function is not differential at point 0. But there is a trick. The trick is, absolute value function, so this is a linear function on this interval and linear function on that interval. So it's a piecewise linear function. So by doubling the number of variables, you can convert this function into a linear function. The price that you pay for that, if your x vector had million variables, now it will be 2 million. But in that case, you converted this into a linear function by the trick, which I can write precisely if you want, and you are getting rid of the non-differentiability. But you don't need to know the trick and you need to do that reformulation in order to get rid of the differentiability. If you name this trick your absolute value function, yeah, it may chop at the point 0. There are all these interesting tricks there, but even if you don't know the trick, you can already start asking the right questions. Why people tend to use this MSE error, mean squared error, instead of mean absolute error? just because mean absolute error function is not differentiable. So you need to do reformulation, but in that case you need to know about the reformulation, you need to put it into the code or find the solver in Python that does the reformulation for you. Reformulating this into the piecewise linear function. And then after that everything is great. It's all there. Unfortunately, I know we need to go through this today, which is boring. Hopefully it's understandable because tomorrow we'll move to applying this to practice. All these functions and stuff like that. Any other questions? I know, bear with me, so it's a late time of the day. So don't hesitate to ask questions. Everything that I'm talking about is here in the practical application data science, otherwise I wouldn't mention it. Why to bother you with something that at least I don't see the application for? All the mathematics that we are reviewing is not for fun, it's not for theory, it's because it's applied. And the next 2 days, tomorrow and Sunday, we'll need to project back to the mathematics and see, okay, this is because of that, this is because of that, this is because the function is convex, this is because the function is not convex, or this is not differentiable, what can we do? Which function do you prefer to work with? Quadratic function, absolute value function, or the logarithmic function, or the exponential function, and so on and so forth. It's all there. Unfortunately, basic mathematics is required. So anything which is beyond the understanding, let me know. We'll go through it in a different way. And I know that after 11 hours of studies, that's already difficult. For me as well. Even so, I'm talking. I'm not thinking. Okay, a couple of things for today so that we finish. Point-wise maximum of convex function is convex. So what is point-wise maximum and why that holds? So if we have two functions like this function and this function, what is the point-wise maximum? We take any 2 points and we need to take the maximum. So what is the maximum of these 2 points? This one, yeah? So what is the maximum of these 2 points? This one. So this is a piecewise point maximum function. And if these 2 functions are convex, this function is also convex. Why? How we can show it visually? That's what it means, max of the 2 functions. One interesting thing that we still need to discuss is this: what is the relation between function and the set? Set, množina, I guess in Ukrainian. One interesting thing. So, this is a graph of the function. Everything, the set above the graph of the function is called the epigraph. So this is the epigraph of the first function. Everybody with me? Everything above the graph, which is a set, is called the epigraph. If the function is convex, its epigraph is also a convex set. Well, this is a convex set, as you see. We'll still need to define it more precisely. Now, this is the epigraph of the second function, which is also a convex set. Now, intersection of the 2 convex sets, which is this set, is a convex set, and that happens to be the epigraph of our new function. And that's why the function is also convex, because its epigraph is a convex set. I am sure that at university you have seen these Venn diagrams. Have you seen this? And that's exactly the thing. So this is a convex set. This is another convex set. Intersection of the 2 convex set, which is here, is a convex set. Now that, we will explain all that, and this is how it's used in data science. Это может быть сверху 2 функций, yes. No, не если, это если. Yeah, if you take this as some quadratic functions and do from the top, yeah. And that's exactly going to be the epigraph, or the epigraph, the level set of these 2 functions. When they intersect these 2 functions by the hyperplane. Now, what is, now we need to figure out what is a convex set. So, if you take this set, so convex set, if you take any 2 functions in the set, connect those by the line, and every point on the line is in the set, is called the convex set. Now you take these 2 points, that's a convex set. If we have a set like this, you take this point, connect by the line, this point is not in the set, it's not a convex set. Everybody with me? So, property is intersection of the 2 convex set is convex set, and that's what we have here to show informally that the intersection of the point-wise maximum of the 2 convex functions is a convex function. This property. Why? As I said again, the epigraph of the convex function is a convex set, the epigraph of the second convex set is a convex set, the intersection of two convex sets is a convex set, and that happens to be the epigraph of the pointwise maximum function. So that's why pointwise maximum function is also convex. And the last thing which probably helps to establish the relationship between the function and the set. So if the function f of x is convex, its sublevel set f of x is less or equal to any number alpha is convex. Let's do that as well. Let's start from this function. So this is a function f of x. So what is the level set f of x less or equal than, let's say, alpha is equal to 25. Alpha is any number. What is that? How that set looks like? Let's say this is 25. Okay, we intersect by this, less or equal. So this is the set. Yeah, this is the level set of the function. Function value less or equal than 25. That's a level set that is convex. Because why? Definition. Take 2 points in the set, connect by the line. Every point on the line is in the set. How about function of 2 variables? 25. Intersection by the set is a hyperplane, yeah, in our case. So what we have this. That's a level set of this function. If the function itself is convex, this set is convex. How about if we are, instead of less or equal, if I put equal to 25? Anything changes? Let's think. How this set looks like. We know how this set looks like. It looks like this. How about this? Equal to 25 instead of less or equal? That's a ring. So what happens? I will throw it under this. It looks like this, but it only includes the border in the set. Inside is not included, yeah? Equal to 25. Is it a convex set or not? Well, let's use the definition to verify. Nothing to think about. We take this point, which is in the set, this point in the set connected by the line. This point is not in the set. That's not a convex set. Always think geometrically, as I said. Nothing more than visualizing stuff. At least 90% of everything we can visualize, except maybe for the determinant. Maybe we can visualize it as well. We need to check it out. That was a good question. I'm always looking for good visualizations because that helps to understand it for myself as well. And part of their conversations with US students, it helped me to understand some of the things that I never thought about. That's why don't hesitate to ask questions. Even if I don't know the answer, somebody else may know the answer, or we can look it up. But visualization is the key of everything that you want to understand in mathematics and data science. When you visualize, you understand. If you never draw this, you can figure this out. You never know. But this is something that we also call the level set. This is a level set of a function. Along this curve, function value is equal to 25. Yeah, but that's not a convex set because it's only the border that is included in the set. It's equal to 25. It's not less or equal. That's why the inside is not included, not a convex set. That's why in optimization, that's very often used in the optimization with constraints, because so far we talked about unconstrained optimization, minimizing the function. What if we have a constraint of this form? If you want to check if this optimization problem is convex, so this is objective function, is a constraint. Constraint is a set, g of x less than 25. And of course, we want our optimization problem to be convex. What it means, we want our function to be convex and our set to be convex. Now we have the way to verify if the set is convex. If this function g of x is convex, we know that this level set is going to be convex. Cool. So if the function f of x is convex and the function g of x is convex, this is a convex optimization problem. Because the objective function is convex and the constraint is convex. And think about what happens if this is not convex. So let's say I want to minimize this function and the constraint set to look something like this, not convex. Oh, that's a difficult problem. Because if I, going to be here, what do I do? I don't know what to do with non-convex objects. My algorithm will have many difficulties solving non-convex problems. So, good to understand the relations between functions and sets as well. And that's one of the useful properties. And the last thing, which is very much related to neural nets, that's why it's here. We are back to our composite function, the chain rule. So that's, as you remember, something which we call the composite function. How do I verify if the composite function is convex? And that's where we are coming to our favorite neural net. Again, as I said, will be more understandable tomorrow, but so far, the neural net is a couple of nodes. Here we have the function h, here we have the function g. Here we have the function g2, but let's ignore it. Here we have our input y, here we have our input x. Or even let's ignore this part. We have very simple neural net, just like this. Feed forward, very simple neural net. Let's not overcomplicate. This is just my neural net, yeah? X, after we take the function g, and after we take the function h, and that's out. So, y is equal to this function, it's equal to h of the g of x. This is the function that represents this neural net. Give you some heads up for tomorrow, day after tomorrow. Now we want to check if this function is convex or not. How we do it for the convex function? Okay, we know that we need to verify the hash. So let's compute the hash of the composite function using the chain rule. Let's start with the first derivative. What is the first derivative of this function? We have written the chain rule, so it's going to be h prime multiplied by g prime. And just simplify, yeah? Remember that? Chain rule formula. But now we need to compute the second derivative of that. This is what? Product of two functions. How we differentiate product of two functions? U multiplied by v. It's u prime multiplied by v plus v prime multiplied by u, yeah? So we need to do that. Okay. Now, how we do it? So first, we need to compute the second derivative of the h prime using the same chain rule as before. So it's going to be h2 prime multiplied by g prime. Yes? Yes. And now we need to just multiply by g prime because that's this plus the opposite. So we need to take second derivative of g and just multiply it by a. Yeah? Am I right? Looks like you can verify that I'm doing the same. Of course, this multiplied by this is just g prime squared. Yeah? The derivative of function g squared.
Are you missing the thing? Is that finished?
I think I'm not missing the thing because looks like it's inside this formula here, which is the same figure. That's my way to verify it. So when I derived it right now, I didn't look at this. So that's another way to verify. Again, let's do it one more time.
Verify by checking with the answer.
So first, what we need, so the derivative of the composite function. So f was f of x was equal to the h of the g of x. So in the chain rule tells us this, the first derivative of f is h prime, of course, of the g of x. I'm just keeping that notation, multiplied by the g prime of x. If you want, you can just write it down with a more complex, in a more precise manner. Now we need to differentiate this one more time. And because that's a product of two functions, so we need to differentiate this multiplied by that. That's the first part, and the opposite. We need to differentiate this one more time multiplied by that. So, this, applying the same chain rule, so derivative of this will be, we need to differentiate one more of x. So that's what I have written here. And of course, we need to put g prime there, the argument. And after that, so we need to multiply by g prime again. Yes. Okay, because that's staying there. So this is this. And after that, we need to do the opposite. We take this and differentiate one more time, second derivative of g, and this is just rewrite as before. It's u, so h, who's correct. So now, we want this, which is second derivative multiplied by g prime squared plus h prime multiplied by g 0. Of course, we want f to be convex, so we want its second derivative to be greater than 0, or greater or equal, if you want. So we want Hessian to be positive semi-definite. Now, when this sum is positive, it's either, when let's start with this. So this is always positive, yeah? Any number squared is always greater than 0. So that's why, so we want the case when it's all positive, and this component is positive, and this component is positive. In that case, the sum is also positive. So we want this to be greater than 0 as well, in order this multiplication to be positive. Here, we have two cases. Either we want this greater or equal and this greater or equal, or we want this lesser or equal and want this lesser or equal. Yeah? Everybody with me? Now let's write what this case means. This doesn't mean anything because it always holds. Now, h2 prime is greater than 0, so we want h to be convex. Yeah? In that case, its second derivative is greater than 0. So that's why what we want h to be convex. Always. Otherwise, it's not going to work. So, now, two cases here. In this case, you want g to be convex, so its second derivative is greater than 0. And we want h prime to be greater than 0. So what it means h prime first derivative greater than 0? The function is what? Increasing or decreasing? And its first derivative is, again, if you don't remember, do this picture. So first derivative is like this is positive. So the function is increasing. Yeah? Over here it's negative. The function is decreasing. So h prime in this case is greater than 0. Yeah? In this case, h prime is lesser than 0. So this is increasing. So we want h to be increasing and g to be convex. G convex, h increasing, not decreasing, which is increasing or 0. That's the first case. In the opposite case, g should be lesser than 0, which means g should be concave, which is the opposite of the convex. Minus 1 multiplied by convex is concave. And this h is going to be decreasing or non-increasing. So we want h to be non-increasing and we want g to be concave. So we derive these two cases in which function f, the composite function, is going to be convex. The function h is convex if g is convex, h is convex on decreasing, or when g concave and h is convex on increasing. And that's what we derive from that by using this analogy and considering these two cases. A, B. Just the identifications that I get from work. Now we can apply it to some examples. So, let's do for the function, exponential function to the power any g of x. So, in this case, function h is exponential function, function g is just any function. So, exponential function, is it convex?
Yes.
Yeah, so in that case, because exponential function is convex, it's satisfied both definition 1 and definition 2. So, this function, exponent to the any power, any function is always convex. Everybody with me? So, now if you see x exponent to the power x to the power 25 or something like that, it's always convex. You don't need to bother even checking that x to the power 25 is convex or non-convex. You know, as soon as it's exponential function, that is always convex from this rule. Makes your life much easier. Okay, how about the function 1 divided by the g of x? So it's going to be, so what is, and on the positive word. So how it looks? So 1, so it looks like this and this, but we are working on the positive word. So this is convex. Yeah, function h is convex because it's 1 over x on the positive word. And so, yeah, h is convex. And how about is it? So this is non-increasing, yeah? So it goes down. Non-increasing is here, so g should be concave, yeah. G should be concave in order for this to work.
But it is not differentiated at 0.
Sorry?
It is not differentiated at 0.
Or it will never reach 0, so this is asymptotics. Yeah, it's not defined at 0, it's infinity at 0, which is still fine. Yeah, it's not differentiable at 0 because it's asymptotic, it goes to 0 and derivative is just large number. Yeah, that's right. And that's why it says on the positive domain, so we are not including 0 in the domain where it's going to hold. Okay, g to the power p. So our function h is x to the power p, where p is a number greater than 1. So x to the power p, where p is greater than 1, like 1, 2, 3, and so on. on the positive order. So how that's going to look like? It's going to be convex. So x to the power 1 on the positive order is convex. Or square is convex. Cubic is convex. Yeah? On the positive order. That's complex. That's the term of this will increase that time. So the function h, which is x to the power p, is always convex on the positive order, because it's always convex, and it's also non-increasing. Yeah, it increases, non-decreasing. So this is the first case. G should be convex. Yeah, G should be convex from the definition. That's how we can interpret those fields, and it makes our life to verify these type of functions easier for convexity. And the last part for today, so basically just additional examples so that we understand more. Now, show that this function is convex and solve minimizing this function. That's a nonlinear function. Now, so what we can do, we can compute a second derivative to show if it's convex or not. First derivative, second derivative is exponent to the power x plus 1, because exponent to the power x is always greater than 0, plus 1 is even bigger, so it's always greater than 0, so this function is convex. So we were to verify convexity by just computing the second derivative. It's Hessian, not that difficult. Now, how do we minimize this function? Because we know it's convex, we need to find the point where the first derivative is equal to 0. Yeah? So we need to, first derivative of this, which we just computed, is equal to 0. We need to solve this nonlinear equation. The first derivative of x is 0, which is exponent to the power x plus x equal to 0. How we solve it? With one of the algorithms, like this Newton method, which is able to solve nonlinear equations. Now, find the local global meaning of the function if it exists. So for the function minus the logarithm of x, and it's always good to visualize. So minus the logarithm of x is first derivative, it's minus 1 over x. So derivative of the logarithm is 1 over x multiplied by minus 1. Minus 1 over x. And now the second derivative is 1 divided by x squared, which is strictly greater than 0, because x squared is always non-negative on its domain, when x is greater than, is not equal to 0 actually. That's how the function looks like. So we can see visually that it's convex, and we verify it by computing the second derivative. How we find the point of minimum? Minus 1 over x equal to 0, x goes to infinity. So the minimum is reached at infinity, that's asymptotics. So that's what we can see for this. So function x multiplied by the logarithm of x, and this is the graph. So we see that it should be convex. We can verify the same. So first derivative is 1 plus the logarithm of x, second derivative is 1 over x. Greater than 0 on the domain of the logarithm of x, so the domain of logarithm of x is strictly, x is strictly bigger than 0, so strictly convex function. To find the point of minimum, we need to solve the equation first derivative is equal to 0, which is 1 plus the logarithm of x equal to 0, x is equal to 0.37, that's the point of minimum. First derivative is equal to 0, when we solve this nonlinear equation, for instance with the Newton algorithm, we find the point of minimum. And we have that actually in the Jupyter notebooks, which overview tomorrow if you want. Minus the square root of x looks like this, looks convex. We also verify, yes, it's a convex function, and of course the minimum is reached at x going to infinity as well. So this function of two variables, and we compute its gradient, first derivative, Hessian, second derivative, verify that the Hessian is positive definite, which means that it's a strictly convex function. How we find the function? That's basically the first derivative, the gradient is equal to 0, and we can easily solve because it's not in a system of linear equations, it's even simpler. x1 is equal to 2, x2 is equal to minus 1, so that's a global minimum of that function. How this function, x minus 2 to the power 4 minus 10 to the x to the power minus 2 squared, as you see, this is not a convex function, it has two local minimas, and you can show it by computing the second derivative, and finding that it can be the second derivative depending on x can be either positive or negative, so this is not a convex function, and that's what the plot shows. It has two local minimas. This local minimum and that local minimum. But because it's very flat, at this area it may be difficult to find those local minima. That's another problem of some functions. This shape is really see it. And the last is example of the Newton method. So what is shown here, how you do one iteration of the Newton algorithm to minimize this function of two variables, nonlinear function of two variables x1 and x2, starting from the point x0, which is 1, 1. And we need to do one iteration of the Newton algorithm and compute the point x1. So essentially what we need to do, we need to apply this formula to do one iteration. We know x0, we know the function, we need to compute x1. Everybody with me? Now, of course, for that we need to compute the gradient of that function and the Hessian. Again, this function, yeah, it's a bit complex, but not that much. So we compute the gradient and the Hessian, and after to apply this formula, now, as you see, instead of inverting the Hessian matrix, what we can do, we can solve a system of linear equations. So let's denote it by, just to see how that's going to work, I'm just going to rewrite this formula in another term. So, this second derivative inverse multiplied by the first derivative at the point 0 is equal to x0 minus x1, yeah? So what we have, this let's denote as a minus 1, this denote as b, this denote as x. So what we have, x is equal to a minus 1 to b, but we know in order to find this x, we can just solve this system of linear equations. So all what we need to take this without inverse. That's our matrix A. So the Hessian is our matrix A is just the Hessian, multiplied by the unknown x, equal to this, equal to the gradient. And now when we find x, we just subtract x0 and we get the next point x1 when we find this unknown by solving the system of linear equations. That's just a trick. We don't want, as I said, to invert anything, we just want to solve a system of linear equations. So the system of linear equations that what we get, very easy, we find the solution after we subtract x1 and we get 0.5, 0.5, that's a new point, and we can verify that function value at the new point x1 is smaller than the function value at the point x0, which is expected because we are minimizing, so the function value in the next iteration should be smaller than the function value in the previous iteration, the sanity check. That's pretty much it. That's all what is good to do for today. So good to stop at this difficult point so that tomorrow we'll start from something easier and start practically applying all this stuff. Yeah, we may still tomorrow look at some of the Jupyter notebooks for the basic mathematics, how we do all these things in Python, but that's going to be much easier because we know more derivations and things like that. And again, I know that for the first time it all looks complex, but it's not as complex when you see it multiple times and you see how it's applied and you do it yourself in Python. So it's all understandable. And again, we are not studying mathematics for the sake of mathematics. It's all about understanding the data science algorithms. How long those run, which results we get, how we interpret the results. Is the solution unique? All these questions we should be able to answer as professionals working in data analytics. When we run those algorithms, we got some numbers and we have no idea are those a true solution or maybe there is a better solution or should our algorithm run for 1 day or maybe it converges in 1 minute and how we interpret and how we explain the results, how we validate the results without understanding this. That's, in my opinion, it's impossible. I know this is hard, I know this is mind-blowing for the first time, but basically when you visualize, when you write it down, when you look at it in Python, so that's all eventually, by the end of this program, should be understandable in your head. I don't necessarily claim that by the end of this course you will understand all this, but at least we are making that step towards understanding of statistics, mathematics for data science, machine learning algorithms, and all other algorithms in this course. Again, this is not the last course in the program. You will have another 4 core courses and another 4 elective courses, and many of those things will be explained, repeated, or explained from another standpoint in those courses. So you don't see it for the last time, you may see it for the first time, or you may have seen it before, in the intro to the mathematics course. So who took the introductory mathematics from Tatiana Manchas? Okay, 0 of you. So some of those things I'm sure were there, yes?
Yes.
And probably she explained it from another standpoint. Now when you combine it from this standpoint, hopefully it's getting more understandable.
It was quite good, yeah.
Sorry, it was
It was quite good from Tatiana.
great. So is it helpful on the top of what Tatiana has explained, or?
Yeah, sure.
Okay, that's great. So let's stop here for today. We're 5 minutes over, but that's okay. I think everybody can.
Imagine, the name of this course is Introduction. This is only introduction.
No, you see, that's another problem. So I wanted to put things there, which hopefully help you in the other courses, because I'm not sure how good it was explained and if you will see it later. So I try to, and that's a problem. I try to put more than probably necessary in the introductory course. But my hope is that eventually, when you see it another time in another courses and when you work on it, it's gonna to be more understandable this time in your head, because nobody says that data science or AI is one course. It's a combination of courses, it's a combination of the projects that you're going to work, it's a combination of the business cases that you had at your job, that's a combination of successful implementations. And well, let's work on that, on the full stack. So this is full stack data analytics, both from the business side and the technical side. At least that's what we want to do. Sorry, back folks. And sorry for the long day. I know this is a bit too much for one day. Maybe it's a bit too much for 2 days.
So we'll see you in 13 hours.
Thanks a lot.
Yeah, and see each other at 9 a.m. tomorrow. But tomorrow is going to be shorter because today we have one extra lecture. Tomorrow we have one less lecture.